Okay, hello everyone. I decided I would make a brief screencast to help supplement your notes about falling with friction, or as I like to call it, non-free fall. The reason why I'm doing this is because it's not a topic in your textbook. So in case that you needed an extra chance to hear the same material in class, or needed to hear it like on your own where you could repeat it or replay it, now you have an opportunity. So basically, the idea is this: when you do consider friction, when you don't neglect friction, as the textbook tends always to do, that means that you have an object that falls for a brief time at free fall. That is, gravity is the only thing that accelerates it. That's this case right here. So this is falling initially, where gravity is the only thing that's acting. But then, after some time, the force of friction, because more and more air particles knock into the object, the force of friction eventually catches up. And while it never slows the object down, it reduces the acceleration to zero, so that the object reaches what's called a terminal velocity. And so that represents, at this stage right here, so beyond terminal velocity, velocity is constant, and that's what's called the terminal velocity. Those two arrows, they represent sorry about that. Those two arrows represent the force of friction and the force of gravity, and we'll talk more about arrows like that later. But the next thing here, for our purpose, is to talk about the factors affecting terminal velocity. And you'll recall in class I gave you three. Sorry about the outside noise. There might be somebody mowing their lawn or something. One is shape. Basically, if an object is more aerodynamic, that is, the air flows around it more readily, then there's less of an effect of air friction. So more aerodynamic means less friction, and it means a larger terminal velocity. Secondly, we have cross-sectional area. Now, you'll recall in class, cross-sectional area is different from surface area. Cross-sectional area is the slice, I'll write it down, the slice of a volume that is perpendicular to the direction of motion. So a falling sphere has a cross-sectional area that's a circle. A falling person has a cross-sectional area that could be anything. It depends on how you fall. If you fall feet first, then your cross-sectional area might be a small oval. But if you fall like screaming with your arms and legs waving, then the cross-sectional area just looks like a chalk outline or something. This is distinct from surface area. This is only cross-sectional area. And the third factor that affects terminal velocity is mass. Let me go back and include this. So a large cross-sectional area means a small terminal velocity. And with mass, basically because a more massive object, it takes longer time for the force of friction to catch up and to become as strong as gravity. Larger mass means larger terminal velocity. That is, less friction. Cross-sectional area, the smaller the large cross-sectional area means more friction. All of these are logical, so they're nice to think about. Now, the next I wanted to mention the direction of motion. That is what the motion actually looks like, and you can think of it as being in two stages. Now, I'm going to call this a two-stage approximation, and I'm going to do it without underlining. I'm calling it a two-stage approximation because what actually happens is a gradual approach to terminal velocity. But it's a really, really good approximation to assume that at first you have only free fall. So you can ignore terminal velocity and friction entirely until you reach terminal velocity. And then beyond terminal velocity, you have constant velocity. And that velocity is the terminal velocity. So on a velocity versus time diagram, it looks like a trapezoid. You have one area of constant acceleration followed by an area of constant velocity. And it's not a bad approximation to assume that shift, that transition from constant velocity to from constant acceleration to constant velocity is rather abrupt. Now, to help illustrate what that means, I thought I would do a couple of sample problems here, which I'll show you now. First of all, how long does it take an object with a terminal velocity of 70 meters per second to fall 1,500 meters? Now, I'm going to ask for these kinds of problems that you assume the acceleration of gravity is 10 meters per second squared. So that's our acceleration. And so there's two stages. In the first stage, the acceleration is equal to g. And we can use our equations of motion for falling in free fall to calculate how far it's going to fall and how long it's going to take. And then in the second stage, the acceleration is equal to 0, and then the velocity is equal to the terminal velocity. So the first question you need to answer when you're given a problem like this is to ask yourself, well, if its terminal velocity is 70 meters per second and it's falling the 1,500 meters, how far would it need to fall before it reaches terminal velocity? Because if it reaches terminal velocity beyond 1,500 meters, then there's no need to assume to include friction at all. So let's check it out. So first we need to answer the question, how long and how far to reach terminal velocity. So we use our two equations here that we use for free fall. And those are distance equals 1/2 at squared, and acceleration equals v final minus v initial divided by time. So distance equals 1/2 at squared, and acceleration equals v final minus v initial over time. Where in this case, the first thing we need to do is start with the second one. So our acceleration is 10. Everything's moving down, so you can assume as well that down is positive, that 10 is equal to 70 minus 0 over time. And therefore, our time is equal to 7 seconds. So it takes 7 seconds to reach free fall. So we can figure out how far it travels in that time. And so the distance is equal to this one right here, 1/2 at squared, which is 1/2 times 10 times 7 squared. Which is 1/2 times 10 times 49, which is 5 times 49, so that's 245 meters. So falling for 7 seconds in free fall, you would cover 245 meters. That's pretty far, but that's not far enough to reach terminal velocity. So after 7 seconds, 245 meters covered. How much is remaining? 1,500 minus 245 meters are remaining. So in the second stage of the motion, you're now moving at the terminal velocity. Well, now we just use distance equals velocity times time, because that's the velocity that you stay at for the rest of the way. So we saw, remember, that the 1,500 minus 245 meters, that should be equal to 1255. There's 1255 meters remaining. So we can say our distance is equal to velocity times time. And the distance is 1245 equals 70 times time. And so we take our 70, getting the calculator here. Pardon me a second while I get the calculator. There we are. 1245 divided by 70 takes an additional 17.8 seconds. So time equals 17.8 seconds. And therefore the total time to reach ground would be 7 seconds plus 17.8 seconds, which is now 24.8 seconds. That's the total time it would take to reach the ground if you have a terminal velocity of 70 meters per second. You just have to find the distance and time when you get to terminal velocity, and then everything else makes logical sense after that. The second question I wanted to ask refers to a lab that we did. How much distance and time would it take for a coffee filter to reach a terminal velocity of 1 meter per second? Now, the reason why I'm doing this one is we actually did this in class. We actually dropped a coffee filter, and while I slowed it down to 1/8 of a second, you all found that it was moving at roughly, well, it took 8 YouTube seconds to fall 1 meter. So, and it was slowed down to 1/8 times, so it was falling at about 1 meter per second. And I asked, as part of that lab, I asked why I dropped the coffee filter from above the top card. And the reason, as many of you realized, was that the coffee filter needed to reach terminal velocity. So we can see if what I did was correct, like how long it actually takes and how far it moves in that time. I'm just going to copy these equations here and put them down here and fill in the new numbers. This is an easier problem because the numbers are so small. I just thought it would be interesting to look at if it ever comes up. Ah, there it is. All right, so now what we're going to do is our acceleration is still 10, but the final velocity is 1, and so the time is going to be 0.1 seconds. So it only takes 1/10 of a second for that coffee filter to reach terminal velocity if the terminal velocity is in fact 1 meter per second. And the distance that it will cover will be 1/2 times 10 times 0.1, which is 0.01 times, well, it ends up to be 0.1 times 10, so 0.05 meters, so about 5 centimeters. So it took 5 centimeters before it reached terminal velocity, which is what I was telling some of you. The answer is 0.1 seconds and 0.05 meters, that if something small reaches terminal velocity, it does it really, really fast. Hope this helps.